had talk enough before we left the Isle of Lewis that something was wrong at the Flannans. Word had it that a steamer bound for Leith, the Arctur was the name I heard, passed the islands some days past, and marked that the light was not showing. Such matters may be put down to foul weather, or a lamp extinguished in accident, but the way men spoke of it, there was more to the tale. Some said the master swore the night was clear, and still no gleam from the tower. We were meant to sail out on the 20th, but the seas kept us pinned in. It was near a week later, this very morning of St. Stephen's Day, that we stood across at last. I remember we all strained our eyes for a sign of life as the isle came abeam, but no flag flew on the pole, and the usual stores for change of shift were not laid out on the landing. None of the keepers came down the path to hail us. It was queer enough that a murmur went about the deck before the captain even raised his glass. He had the whistle blown, and then the siren besides, to wake the place if the men were asleep or hard at work. When there was no answer to that, a rocket was sent up. Still the island lay silent. By now we were all sure something was badly wrong. Joseph Moore, the relief man, begged leave to be the first ashore. A boat was lowered, and he jumped for the steps with Mr. McCormack and one of our hands close behind. We waited long, watching them climb the path and vanish behind the wall. In time, they returned to the landing and hailed back the news. The station was deserted. The gates were closed, the doors shut, beds empty, and the clock run down. No fire on the hearth. The light, they said, had been readied as if for the night, but never kindled. That set us all to whispering. One man said they'd gone mad, another that they had quarreled and slain each other. Others reckoned the sea had them, for there are places at the West Landing where the waves strike higher than a man may stand. The captain, for his part, wasted no time. He ordered Moore to stay behind and keep the lamp, and called for volunteers. Lamont and Campbell from our crew stepped forward, stout lads both, and Mr. MacDonald, the boymaster, besides. They were sent ashore with their gear, and we watched them go up into the empty place. None of us envied them the lonely vigil they were to keep. When all was arranged, the captain made ready his wire for the board. We heard the words of it repeated about the ship. A dreadful accident has happened. The 3 keepers, Ducat, Marshall, and the occasional disappeared from the island.
The more astute among you might have caught on to that this episode, among other subjects, will deal with the mystery of the Flannán Isle's lighthouse disappearance. It's a classic among fans of mystery horror. Still, I wager that I may be able to show it from an unusual angle. For those unfamiliar, the Flannán Isle's lighthouse disappearance refers to the case when the 3 lighthouse keepers in 1900 went missing from a lighthouse standing on the small rocky island of Elon Musk in the Flannán Isles in the Outer Hebrides off the west coast of Scotland. The case has since drawn plenty of attention and speculation, as the official explanation given seemed inadequate to most contemporaries and to many since. The lighthouse was a sturdy 23-metre or 75-foot high building close to the top of an 88-metre, 289-foot tall cliff. It was finished in 1899. To put the time period in perspective, technology was at the level depicted in H.P. Lovecraft's work. Combustion engines, in this case steam, were slowly displacing the traditional solution. The sailing ship, which was still an everyday sight in commercial use. Legacy technology lingered on. Steam was limited to hauling bulk or timely cargo, or for prestige and military use. If you asked a lighthouse keeper, they would say that steam engines cost too much to run for close-to-shore fishing, or to haul cheap cargo. Telegraph was present in cities and just starting to reach smaller villages, but never homes. Perhaps the local post office or a company office had a line. Or else, you had to walk to the next town to send a wire. Humanity was still very much in the process of conquering nature. The lamp of the lighthouse was lit by oil, needing a fresh barrel of paraffin every 20-ish days. This naturally lent itself to making the arrival of new supplies happen once every month, when weather permitted. The same was true for the rotation of workers. The lighthouse was operated by 3 on-site keepers, and a 4th being on leave, 1 keeper rotating every 20 days. A landing fit for rowboat access was linked to the lighthouse by a steep tramway, a narrow-gauge rail track with the cart pulled by a steam engine with a rope. Other than the lighthouse keepers, there were only seabirds, and the ruins of a small 7th century chapel dedicated to St. Flannán, present on the Isles. The state the lighthouse was found after the disappearance of the 3 men was unusual. 2 of the 3 men had disappeared while wearing their oilskins, what we would today call a raincoat, and one without wearing it. The keepers were suspected to have gone missing in the evening, as the lens was cleaned, the light ready to be lit. They had eaten their dinner and tidied up afterwards. They had gone missing before lighting the lamp for the night. The western end of the island was brutalized by the sea. The iron railings connecting the footpath between the rails and landing were broken in multiple places. Iron beams secured into the rocks were bent. Part of the rail for the cart was ripped out of the concrete. A box that was used to keep ropes for the landing and the cart gone missing from the island from 34 meters, 110 feet high. 60 meters, 200 feet up the rock, the turf was ripped out of the ground as far as 10 meters back from the cliff edge. Since the group of 4 keepers, James Ducat, Donald MacArthur, Thomas Marshall and Joseph Moore, the last not present on site at the time, had been at this job for some time, the public didn't believe them to be foolhardy or inexperienced enough for all of them to be washed away at the same time by a storm. Speculation about the case has been ongoing ever since, from local Scotsmen blaming the phantom of the 7 hunters present in folklore to sailors suspecting a giant sea serpent claiming the lighthouse keepers. Naturally, there is also no shortage of more reasonable theories, including the lighthouse keepers fighting, brawling, and ending up falling off a cliff into the sea, or even one of them murdering the others, then in regret or shame or for fear of the consequences taking his own life. I strongly suspect the official explanation was right. The keepers were washed away. More precisely, they were claimed by what we now call rogue waves, a phenomenon nobody in 1900 yet understood. For a long time, the so-called scientific community handled the stories Seaman told about walls of water hitting ships as nothing but tall tales. Despite what some might say, that treatment didn't come out of pretentiousness. It did have a reason, namely, that waves are how disturbances in water spread. As time passes and the disturbance moves, the wave becomes more and more sine wave shaped. As it spreads out over a wider and wider area, the wave crest becomes lower and lower, as the volume of water in the original disturbance gets spread ever thinner over an increasingly larger surface. Single waves don't just magically increase in height or persist forever. Anyone can test this by dropping a pebble into a puddle. Still, stories about walls of water hitting and sinking ships kept appearing. When in 1826, 74 years before the disappearance of our three men, the French scientist/naval officer Jules Dumont d'Urville and his colleagues reported a 33-meter, 108-foot high wave on the Indian Ocean, no one believed them. The winds at their location couldn't sustain waves higher than 9 meters, 30 feet, according to calculations. Accuracy of mathematical methods to describe waves created by winds improved over the years. As such, the stories about walls of water sinking ships became less and less believable. There was one case when solitary waves traveling long distances was accepted. The so-called wave of translation in a canal observed by John Scott Russell, an engineer of some note and friend of Isambard Kingdom Brunel. This observation in 1834 and its mathematical description laid the groundwork for multiple fields 1.5 centuries later. The observation was seen as irrelevant for ocean waves. The persistence of the wave in a canal could easily be attributed to the fact that canals are mostly of the same width and the same depth along their length. Thus, the wave is not spread thinner and thinner over a larger and larger area as it moves on. Other reports were outright ignored. Yes, the SS München, a 260-meter, 857-foot-long freighter, was lost with all 28 hands in 1978. One of its lifeboats was later found floating, torn away despite being hung 20 meters above the waterline. It was chalked up to severe weather somehow creating an unusual event. Rogue waves remained a myth. Yes, in 1982, the Ocean Ranger, a 120-meter-long, 80-meter-wide drilling platform said to withstand 34-meter, 110-foot waves and 190 km/h, 110-knot winds, sank with all 84 men after water pressure crushed a high window and flooded the ballast control room. In 1995, the Draupner natural gas drilling platform, fitted with scientific instruments, documented a similar encounter and survived to tell the tale. Lasers recorded a wave 25 meters, 84 feet high, while the surrounding wind-driven seas measured only 12 meters, 39 feet. The instruments could not be blamed, for the rogue wave struck hard enough to damage equipment high above the water. Understandably, this created a great deal of interest in the scientific community. The observation contradicted all previously existing theories, and so they had to be overturned. There was work to be done, fame and glory to be gained for whoever could make sense of these new observations. Well, mathemagics have improved much since the days of Russell. Russell's near contemporary, Joseph Fourier, Jean-Baptiste Joseph Fourier, created a mathematical system for describing all waves, on the back of earlier work by Taylor and Maclaurin, who of course had built on the work of one of the greatest mathematicians, Newton. Most mathematicians knew Fourier's series were a thing, some scandalous trick with an infinite number of sine and cosine waves, but outside the circle of analysts, few understood them well enough to actually use them, which meant real progress had to wait until they became common currency, rather than an oddity people had merely heard of. Fourier's series remained largely unknown until the 1920s, gaining prominence with the rise of electrical engineering, and finally, becoming standard knowledge in the toolbox of any engineer when the fast Fourier transform was invented in 1965. After all, it gave a way to force computers to calculate for you, instead of having to do a cursed calculus yourself. God forbid, by hand. Armed with this knowledge, and eager to make a name for themselves, people dug into theories describing waves with a hitherto unseen gusto. Of course, the fact that the mathemagics applicable here could also be used for quantum mechanics likely helped to motivate some. After all, why settle for merely predicting rogue waves when you could take a shot at making the theory of everything? Back to the point, let us not wander too far. In 2016, something substantive for the average seaman was cooked up by those doubtful mathemagicians. It was then that MIT published a method for the short-term early detection of rogue waves, giving 2 to 3 minutes heads up to people on ships and platforms to brace. Let's talk about what these mathemagics look like. You see shown in the illustration. As you add more and more of waves, with just the right height, length and distance between the crest tops, you can get closer and closer to the desired surface shape. If you add some more, you can get pretty decent looking squares. Of course, that's not all there is to it. Part of how ships get sunk is how certain setups of sine waves that make up the surface shape can be pretty resilient to spreading out and can even steal a bit of height from other waves. That's how you get longish-lived walls of water crashing into your ship. Well, if you are allergic to mathemagics, skip ahead to the time shown on screen. For those staying, I won't use anything beyond the 4 basic operations. We won't do the higher mathemagics you've seen on screen. Instead of that elven script, the sort of thing that earns you strange looks at airport security, we'll stick to making a series like you learned in first grade. A series of numbers that can be used to create a series of waves. The first element of the series A0 is just a number, a flat line, not even a wave. You get it by subtracting the area below the x-axis from the area above it. Next come the repeating waves, which in practice aren't much more complicated. We'll take shortcuts to the great chagrin of mathemagicians everywhere. You sample your surface shape at a few points, note the heights, multiply by the height of the sine or cosine at those points, and tally the approximate areas that you base on height of these reference points. Once you calculated that area, divide it by half the length of your original shape, measured on the x-axis, and you got one of the coefficients. For A1, you multiply your desired function by cosine of x, then measure the areas. For B1, sine of x. For A2, cosine of 2x. For B2, sine of 2x. For A3, cosine of 3x. For B3, sine of 3x. I trust you can guess the rest. The resulting series looks like this: A0 plus A1 cos x plus B1 sin x plus A2 cos 2x plus B2 sin 2x plus A3 cos 3x plus B3 sin 3x, and so on. The more terms you add, the closer the sum of waves matches your desired surface. Still, if you've been paying attention, you'll have noticed all these A and B coefficients that describe how tall any given constituent ripples is. Plot them on a coordinate system and you get a so-called waterfall diagram. Among other things, it's a very convenient way to visualize music. See that circle on the diagram? That's the bass drum. You'd never spot it in the raw waveform, let alone edit it. It is magical, but hard. Not in the sense that how understanding quantum mechanics is difficult, more like running a marathon, tedious, laborious. Well, the title did include mentioning that we stole the magic, and I guess by this point, some people might feel lied to. The point is, waves are waves. It doesn't matter if we're talking about the surface of the sea, sound in the air, radio waves, which, like all electromagnetic waves, are just another color of light, or even a chunk of metal vibrating. the same mathemagics that predicts how ocean waves move also works for planning electromagnetic signals. One might say, who cares? Well, arguably you do, if you use a mobile phone. Generally speaking, every kind of modern radio transmission still follows the old Morse code idea. Information is encoded by changing some property of a wave in a way that can later be decoded. The traditional methods were AM and FM. AM, amplitude modulation, vary how loud a steady tone is. FM, frequency modulation, vary the tone's pitch instead of its volume. Both were fine in their day, but they have limits. AM is very sensitive to interference, and FM improves on that, but still breaks down if the background noise is strong enough. Well, those mathematicians did figure a way out to get around this. So let's explain what the Fourier transformation does. You know the thing name-dropped once in this video. It allows us, or a computer, to make a spectrogram of the signal we receive. That's helpful, as then, at every point in time, you don't have a single pressure value, or in simplistic terms, volume. Instead, you get a row of numbers, telling you how loud each tone is at a given moment. This way of depicting the signal is called the frequency domain, whereas the normal, volume-based one is called time domain. Using the frequency domain allows you to make a signal out of a combination of tones, which is helpful as there is less of a chance of random noise looking exactly like the combination of tones you decided to use as a symbol. You can do the Fourier transformation by multiplying the signal stored as a matrix with the so-called Fourier matrix. Matrix is just a fancy name mathematicians call spreadsheets. Matrix multiplication is also known as multiplying numbers in one spreadsheet by numbers in the other one. In the correct order, of course. So, to get the result for any bracket you want to know in the spreadsheet, you take the numbers in the same row in the first spreadsheet and the numbers in the same column as your chosen location from the second spreadsheet. You multiply each pair of them, so first number in the row gets multiplied with first in the column, second in the row gets multiplied with second in the column, and so on. Then you add these results up. Fourier transformation is just multiplying the spreadsheet in which you store the signals with a special matrix. FFT, fast Fourier transformation, is just fancy faster way to do this matrix multiplication. The Fourier matrix is symmetrical, so you don't need to calculate everything if you go smart about how you calculate. One problem remains. You need to spot the correct symbol, and the more elaborate the symbol is, the more a computer needs to crunch number to decide if it sees the symbol or not. Things get very expensive and very power-hungry very fast. Enter the so-called chirp spread spectrum, the trick that makes these nice $1 LoRa radio modules possible. Yes, they're not lying. The range really can hit 10 kilometers. On top of that, one can transmit for 12 hours on a single AAA battery, receive for a day, or sit on standby for 10 days. And that's continuous use. If you only switch it on for a few minutes at a time, the battery can last weeks to months. Let's talk about the dirty trick, because it's beautifully simple. We're going to be sending waves. We pick the number we want to send, write a 1 into that place in the time domain spreadsheet of the signal and perform an inverse FFT on it. Same idea as the FFT, just the opposite direction, using a different special source matrix. Now comes the trick. Multiply it element-wise by a chirp, in matrix form that looks like a diagonal filled with complex numbers, each one a little rotation on the unit circle. This step turns what would be a flat monotone, like in AM signals, into a continuously changing chirp. Put it back through an FFT, and out pops a sharp peak. At the receiver, you do the opposite. multiply by the conjugate chirp, and FFT again. The noise gets smeared across many bins, but the signal collapses neatly into one. As a result, no fancy number crunching is needed at the end. The symbol is just the column with the biggest number in the frequency domain. These tricks are the reason why we can have nice things, like the ability to talk to anyone on the other side of the globe for a bargain price. In ages past, people would have called it magic. As weird as mathematicians' antics can be nice to them. Without them, the world would have way less magic and fun in it.